So, all right. Yeah, so since you are just you guys here, I wanted to actually go through some of the material from last time, the one that was done a little too fast at the end. And I think these two algorithms that one of which we covered kind of, and a related one, are the most popular currently, as of today. Kind of the most popular, one of the most popular algorithms. So it's good to know what they are, at least, how they work, what they mean. And the other thing that is very interesting and that we haven't done so far is model-based RL. So I want to shift from today in the middle of the lecture from what we are currently doing. The current way of doing is model-free reinforcement learning. And we will see what model-based reinforcement learning is. That's the only thing. Today's lecture will be short. I have to, unfortunately, there has been a scheduling error and I have to be two places at the same time. So at 11, I have to be somewhere else. So we will have to stop like 10 before 11, just so that I can make it. Anyway, so that aside, let's begin. So remember what we are doing. Okay, I will do a little bit of review, as I said, of the last lecture, go through the TRPO thing. Then I will explain what the PPO algorithm is, which is pretty related and actually very simple to understand if you understand the rest of the concepts so far. And then we'll start with model-based RL. Okay, so that is the plan for today. So last time we talked about this, importance sampling. So what is importance sampling? It is sampling from a different distribution than what you're interested in. So statistically, it was done to reduce variance. So this is the origin of the subject, and we talked about it in some detail last time, but just to give you a philosophical review of what that meant, is that I don't know how to sample from my own life. You don't know how to sample from your future life. But you see other people who have lived life ahead of you, and you can sample their experience, right? So how do you decide your policy? What we do, what lectures we do, what job we do, what kind of world we live in, what contribution you want to make. You kind of get inspired from other people. So this is basically what importance sampling does. You have access to data from other distributions than what you are currently interested in, but you want to manipulate your current distribution. You want to see how good or bad it is. You want to improve the current policy. So in all these, in whatever follows, there are two policies. So like I think it's written somewhere, but so there is a policy called pi theta. This is the one we want to improve. Okay, and there is a fixed policy, which is your old policy, which is source of data. So unlike supervised learning, in reinforcement learning, data is not stationary. Why is data not stationary? Because the experience you collect depends on your choice of policy, right? So this is where the policy that will generate your experience and that you have used to generate your experience, right? So suppose you should imagine maybe a difficult but really applicable scenario is in robotics, where the robot is moving with a current policy. It's collecting all the data with the current policy, right? But from collecting data, you want to see, whether some other policy would be better. How should I improve some other policy for some other similar robot or something like that? So this is standard procedure. So this is the thing that generates your experience. Okay, so this is where your data comes from, and this is where you want to use. So this is just to bring you line. We are going to review a little bit of the material from last time, including TRPO, and then we'll go to PPO. Okay, that's the plan. Anyways, so okay, so we have talked about importance sampling last time, so I don't want to spend too much time describing what it is. But is it okay to sample for theta? Is it okay to sample from theta old? When is it okay to sample from theta old? So going to a philosophical example, if you want to live your life forward and you want to sample from somebody else's life to see what's a good idea for you, should you sample from someone somewhat close by in some sense, like belonging to the same community, roughly, in the same time, same country or whatever? Or you can sample from someone 5,000 years back from, I don't know, from Mesopotamia or whatever, what their experience was. Are they going to be relevant for you? Not, right? So first thing we want to say, the relative relevance is important. So we have, let's just say, I would remind you, so we have a policy. So this takes in the front, this is the input to the state, right? And it has all the parameters that are we call theta, and it outputs. So you have action one, so probability of action one when you input that state as, probability of action two. So it outputs a probability. This is what a policy is. And the parameters here is what we generically call theta. So this thing represents pi theta. Your neural network currently represents pi theta. This is where it is set to, where the parameters are set to. Okay? But the data you have collected, from which you want to change your neural network, the data you have collected is collected from some other policy pi theta. So is it currently okay to change this neural network based on that data? Right? So first thing we said, okay, as long as these two are not too far apart, as long as theta old is not too far from theta, you can use the data. That's the logic, right? So how did we formulate this? This was the first version. I hope this is the right order of slides. Okay, so all right. So the thing is that to say this is still relevant, you have to consider a kind of objective that you're trying to. So you have a loss function here to improve this neural network. Okay, and that loss function, we have kind of seen this before, but that loss function is essentially given by this formula that we have somewhere here. Okay, so this has been simplified later, but what does it say? It says that you are taking the expectation of probability of some trajectory along the policy theta relative to its probability with theta old, and to which you multiply this either the reward or some advantage function, okay, along tau. So this is your loss function that you want to sort of optimize. So its gradient is what should you want to go to compute. So we computed this gradient also last time actually by hand, more or less. But this is a simple enough formula. So if you expand the pi tau theta as a sequence of probabilities given by the dynamics terms and the probability of the transitions given by your policies, only the ratios corresponding to the two policy domains and the dynamic terms cancel out. So the old objective, trying to find the gradient of that, is same as finding the gradient of this new object. Well, okay, that is more or less clear, right? And now this is a question I think I've already asked you. How good is it to consider computing this gradient from the old data? How good is it to consider gradient considering the old data? Right? And so one answer is more or less was obvious from our discussion last time. Oh, there's something wrong here? No. Okay, good. So you have to find the distance between two densities, two probability densities. Okay? And for probability densities, it doesn't make sense to have a distance between them to say least square or something like that. A good difference between them is the KL divergence. Right? So I remind you what the KL divergence would be. So it will be pi theta. I don't know which order the KL divergence is written here. Theta whole to theta? I cannot see that. Because although people call this a distance, it's not symmetric. So it does matter which one you take first. Although it doesn't, at the end, in the algorithm, actually, it will not matter. So KL of this is basically, it is just pi theta A t given st log of pi theta old of pi theta A t given st. Something like that is the KL divergence. And one can actually simplify this expression quite some bit, but I'm not going to do that. So it's computable from your data in some ways. So remember, you have this ratio here. If this ratio is close to 1, which is what is important, if this ratio is close to 1, the KL divergence is small. Okay, this is in sense what there is. So you want to say the KL divergence is small, and as long as the KL divergence is small, you try to optimize. Given this constraint, you try to find the best theta to optimize your neural network. So this is how good you can use your data successfully. Okay. So is this clear actually? I mean, we talked about this last time too, but before I move on, we'll do exactly the same thing again for one more problem. So I thought it's worth it to review it a slight bit. So if you guys have questions, you have special privileges because you're here, right? Anyways. All right, so this is basically rewriting the old problem that I just written in the slide before it into a new formulation. So what the old slide said is that you cannot have the distance, the KL divergence should be some less than, I don't know whether it was less than some delta. So this was the constraint. optimization, where Lagrange multiplier says, if you know the standard theory of Lagrange multiplier, you should be able to find a beta for which you could put this constraint as the same as having a value of beta for which you optimize this whole thing. This is standard optimization using Lagrange multipliers. Nothing. I can remind you what Lagrange multiplier is, but this is basically always the case. If you want to optimize, maximize, minimize, so if you want to find max fx or x with constraint gx equals some value alpha, then you have to optimize, say, max fx or x and lambda fx minus lambda gx minus alpha. So this problem is same as that problem. This is the theory of Lagrange multipliers. Okay, there is it's pretty much standard in several calculus of several variables, right? Your analysis 2-3 lecture, you should have seen this. Anyway, so this is just a reformulation, but this is what you can optimize. So the constraint optimization is hard to carry on a neural network, whereas this optimization is easier to carry on a neural network, or that's what we think in the first case, right? But the thing is, you still have to compute the scale term. And the scale term is not obvious how to compute it on a neural network for optimization purposes. Okay, so this is the real issue. So of course this looks nice and cool in theory, but the problem is how do you compute the scale terms? What we did last time, and which was much of the discussion, is to show the expansion of KL divergence. There is an expansion of the KL divergence, a Taylor series expansion of KL divergence, which can approximate this term. So if you want to do this optimization, you take a Taylor series approximating the KL, and that Taylor series contains basically the Fisher information matrix. That's all. So you approximate the Fisher information matrix, and you have an algorithm. So that is the standard way of doing this thing, which I think. Oh, what is written here? Okay, that is good. So what this says is you have replaced the KL with this second order approximation of KL, which is the Fisher information matrix. This is something one can compute, and that is a standard theory in statistics, and I don't want to go into it right now. But we can do that someday. But this is very standard how to find value of the Fisher information matrices. So once you have reduced the formulation in this language, use standard calculation for G theta, and then you can optimize it in a neural network. Okay. So this is basically what classically is the first version of proximal policy optimization algorithm. It is still difficult. It still involves a lot of approximation and all that, and it has its problems. But it works quite all right. And there are people people in OpenAI who claim it works extremely well. I don't know that. Anyways, so let's just carry on. So here the problem has come because we are approximating the KL divergence only up to a second order term, right? But what you can look at the formula for KL divergence, and what really matters in this formula of KL divergence is this term here, is this ratio, right? So you want KL divergence to be small. Basically, what does that mean? You want this ratio to be what? Close to? So you want log of something to be 0. You want the ratio to be close to 1. So a sort of crude approach, which is probably also easy to justify, at least empirically, is why don't we try and make this ratio as close to 1 as possible? That would be most obvious approach. And that will solve having to take the second order approximation and all that kind of stuff. So this is the algorithm that is easier to implement than everything else, and basically says, let's just do that. Let's just make this term close to 1 as possible. So this thing is called, I don't know. So I'm kind of a little worried today. I have to exist at many places, so I'm going to be a little faster maybe. So the PPO algorithm says it changes the objective function that you were optimizing, right? So you change the objective function that you want to optimize for theta. How do you change it? So in this old optimization term where you had the KL thing, you want to not think about the KL to give you a region where you are considering the optimization, but you want to consider the region of optimization to be given by this ratio. Okay. So this is basically all that is done. So how do you get a region of optimization from a ratio? So, by the way, do you understand this symbol that whenever one writes a hat in statistics over an expectation or over any quantity, what does that mean? I think I should have written it on the slide, but I know I didn't. What does putting a hat on something mean in statistics standardly? Approximation. What kind of approximation? An empirical approximation. So this algorithm just says, forget about everything, we'll just do an empirical count and divide like you do an integration using law of large numbers, Monte Carlo or whatever. So this expectation is assumed to be, everything is assumed to be empirical in this algorithm. So all right, so what does that give us? Okay, so how do you get, what do we want? We want pi theta of 80 st divided by pi theta old 80 st. This quantity is what we call RT theta. This we want to be in absolute value. Its difference from 1 in absolute value should be less than epsilon. So 1 minus this quantity in absolute value is less than epsilon. And that is say our constraint. That is what we want to implement. So one way to implement it in a nice way, so you could call this as a constraint and use the old. So we had this J IS. So you could optimize this JIS using this constraint. But this does not solve our problem. Now you have to solve constraints separately and the objective separately. So how can you put this constraint inside your objective? In an empirical sense, you can do it. So a clip means, what does the clip function do? So if I provide two values, what does the clip do? It takes the values between, so I have two values minus, so I have my function, say this is, I cannot draw multi-dimensional pictures, right? So this is something theta. Let's just say this is 1. So this is 1 minus epsilon, 1 plus epsilon. This is some theta. Okay. So whenever this goes over 1 plus epsilon, you make this function equal to, so your function that I'm drawing now will be something like that. Okay, so the clip actually clips the function between two values. It does not let it go too far away from the values that you specify. So it forces the two limits, two values on a function. So that is what the clip of a function means, within two values. Okay, so one can write a definition, but it's easy to just see what you mean by drawing a picture. So you have replaced this function by clipping it to the two values, and you can replace r theta. So your objective was actually something like r theta times a hat, the empirical value of the advantage or the return function. So rather than saying you multiply r theta and a hat, you just clip r theta within this range, take the minimum with r theta, and call this your new expectation. So basically what you have done, you have chopped the whole inside of your j, the empirical, in an empirical sense, you chop this to within a bounds for rt theta. So it now does not allow things to be too big, and now you optimize things right from here. Because this term, which you want to have in a constraint, this is precisely also the term in the optimization. So rt theta is what you're trying to do, right? So you expect your j is rt theta times a hat. This is the original j in an empirical sense. So in an empirical sense, the original j was just that. But if you want to put a constraint on r theta, just put it inside it. And that is the PPO algorithm. Okay. So this is rather easy to implement. You can find standard code on internet, so it's not difficult, but you should know what it is doing and why it is doing, and whether it will apply to your problem or not. So for that reason, so the mathematics here is not so complicated. Well, there is no mathematics, at least in this step, there is no mathematics. They just say, just use the empirical formula. That's how our algorithm is. If it converges, good luck. Right? So, okay, so we'll take a break from this. So this is, so far, we have covered two ways of doing RL. The first way of doing RL was to compute a Q function by Monte Carlo or TD or other methods. Right. So I'm going to just pause this for a second. Is this recording? I hope. Because last time I didn't record somehow. So we have seen two ways of doing RL so far. One was Q learning, Monte Carlo. And the second way we have been trying to do now is policy. So directly learn policy from experience data. Okay, so these are two ways of doing things that we have considered so far. But in the background, we have assumed something. In the background, we have assumed that we have an MDP. You remember MDP long time back? The MDP is your image of there are states and actions take you from one state to another state and they get you some reward. Right? So an MDP was state, action, a transition probability, reward, and okay, a choice of a gamma, which I'm going to is independent. So let's just forget about it. Okay, so this is what's in the background, but we have never tried to learn this object. We don't care from which state to which state, with what probability do we transition. In all these algorithms, this MDP of the real world, right? How I live in this world, there is some way the world is interacting with me, but I'm not trying to figure out the model of the real world and how it interacts in any of these problems, in any of these algorithms. So these are called model free. So these are model free. They don't need to know what the world is, how the agent and the world interact. They don't need to know the P. And they also don't need to know actually R. All they need to know is how this R accumulates in Q or in pi. Okay. So what will we now do? We will now consider a way in which we actually try to understand what the underlying MDP is. Find an approximate. Well, one can never find what reality is, right? There is the classical statement that one will never understand the reality. So we'll have to find an approximate MDP that approximates the world, and then use that MDP to solve the problem of finding the optimal policy. Okay? So that kind of an approach is what we are interested in. So the next thing is what one calls model-based. Okay? So far we haven't done it, so we now have a look at it. Oh, this thing has separated into two pieces. I don't know what I have in front of me. What happened? Okay. Okay, so I think this slide basically probably only says what I have just explained, but still, let me just check. So when we talked about models in the beginning, actually when we did the maximum likelihood estimate and KL divergence and all that. So what is a model? In mathematics, what is a model? Do you remember? A model is a bag of possible things that can fit the world. Right? So when we say we're trying to model something, we start with a range of things, one of which is probably best suited to fit the world. So in this case, you fix your states, you fix your actions, you say, okay, there is various possibilities of transitions between these, but I will only consider some of them, which I will parameterize by a parameter eta. Okay, so these are some possible transition probabilities parameterized by some parameter eta. Okay, and similarly, there are some possible rewards parameterized by eta. Okay, so in this model, we start. Okay, you could also say, oh, how do you know all the states, or how do you know all the actions? You could also parameterize them. To be really honest, and people do that, but that becomes too complicated. So let's just start with something simple. So we'll consider a whole collection of MDPs. Well, we don't know what the transition probability is, so we choose a whole bunch of transition probabilities. We don't know what the rewards are, so we choose a whole bunch of rewards. So these two things, one of this is a density, probability density, one of this is a reward, a scalar, a function, right? These two things are what your neural network will now represent. Your neural network will now represent these two objects. Okay, and you want to find the best eta, the best parameter value eta, for which you are as close to the experienced world as you can be. Okay, so this is the goal. The goal is to use the experience to find the best value of these parameters in your neural network, so that you have the best possible fit to the reality. Well, you are not trying to fit everything. You have made some decisions in your model. When you said you can only choose between these, you have made some decisions. And one has to live with that. That's how modeling works. All right? Okay, so I think that part is more or less clear. Is there anything else that's... So this transition probability, so whenever we have unknown functions or unknown densities, we consider them as a neural network, say for example, or some other linear model, a regression model, and you try to find them. That is the whole point of, that is how the machine learning comes in, right? You're trying to learn these two possibilities. So how can we best do it? So let's just consider the most obvious situation. So you collect, so there is no policy now, okay? There is no policy, you're in a state, you go to take an action, you get a reward. You are in the next state, you take an action. This action has not been chosen by a policy, just arbitrary action. Okay, so far we have been trying to optimize the policy or something like that, but there is no policy here. We just arbitrarily take a next action, collect next reward, end up in a new state. No policy involved. This is just your experience of just randomly, without any policy, going around in the world. So if I walk around and I walk into this wall, I get some reward. And if I don't walk into the wall and turn away, then something else happens. So you just learn whatever experience without any policy, right? And whatever you collect, you can consider this as state action. Starting with a state and an action, you end up in a new state and have a reward. When you start with a state and action, you end up in a new state and a new reward. So you can consider this as a mapping. State action maps to reward and state. What can you do with the mapping when you have such a data? This is now a labeled data that you have collected. Right? This is now a labeled data. And whenever you have a labeled data, you have a supervised learning plot. So you can try to now, basically whatever you have learned about supervised learning, however you want to make your neural network, you could basically do that. That is what this means. Okay. All right. So okay, what is? We'll at least get to that, I think. So, by the way, I'm going to leave a little earlier today. So, so the point is actually that you might think, this is one input and two outputs. Why not just train two neural networks independently? Right? So you can say, oh, from state and action, I learn a reward. The state and action, I learn a probability of getting into a new state. Right? So I can put this into two neural networks separately. Okay? So this is often done. It's not always done, but it's often done. And if you make this assumption, what have you made an assumption of? You made an assumption of some conditional independence. So if you separate these two things into two separate neural networks, first thing to observe is that which one is which? I cannot see. So okay, the state action to the state, the second one, as it's listed here. State action to state is a probability learning problem. And when you have a probability learning problem in a neural network, what kind of a loss function you should use? Something that tells you the distance between, not points, but distance between distributions. So one example we already learned in our course. So that's how I wanted to put it. So when you design that neural network, your loss function should be a KL divergence. This is a general fact. Sometimes people forget about it. When you try to learn a distribution, you should use something that separates distributions, like KL divergence as your loss function. And the first thing is not a distribution. So you could use something like the usual least square error or whatever as your loss function. Okay, so one should remember this difference between these two neural networks, even if you separate them. But you can separate them if you make this probabilistic assumption that the joint probability of getting into a state and a reward is independent of the two things. So it's same as the product of the probability of getting into a state from the action pair, action state pair, and probability of getting the reward in the action state pair. So if you make this assumption, this is fine. So is this assumption always true? So for example, you have job offers from 10 companies. Each company, Amazon will pay you a lot of money, but it will take you 80 hours a week to work there. Another company will pay you less, but you have a much better life, so on and so forth. When you make a decision like that, you cannot choose a company, which is your state that you choose, and your reward. They are coupled together in many situations. So whatever state you go to, transition to, so you choose a job at a high-paying company like Amazon, you automatically, your lifestyle reward changes. And you take an offer at a low-paying, at another, say, lower-end company, your life reward changes. So this assumption is not always true. So often you should model this as a combined thing. Of course, if you look at people talking, they will always tell you to separate them, but that is not true. This is not how it works. But often it's a reasonable assumption. Very many times it's a reasonable assumption to train two separate quantities. One using some regression algorithm because it's a number, and second approximating some density with a KL kind of loss. All right. So there is an assumption when you separate these two, this supervised learning problem into two different supervised learning problems. It may or may not be true for your problem. Okay, so now we have done one thing. So assuming now you have a network and you have trained, you have found the best parameter errors. So let's say found the best data to fit the experience. So we have now an MDP. Let's just call it data best. So now we have an MDP. Guys, are we done finding an MDP? Is our job done? Not really, right? This is the beginning of the job, honestly. So once you have found the best MDP given your experience, so this is the best given your experience and your model, of course, right? So there is a conditionality here, condition to given experience and modeling. If you choose your new modeling, you can get another thing as the best object, but it doesn't matter. Let's just say we have obtained this thing. What do we do next? We have to do a planning. So from this, we have to now generate Q or pi. Well, if you generate Q, you will also generate pi, but one of the two is what we want. And that thing is called planning. When we have an MDP, converting it into that is called the planning problem. So this is your choice of, there are many choices of actually doing the planning. Okay. You could, if you have small enough process, then you could do it, you could directly solve the versus equation. Do you remember what that equation was called? Suppose you have a small MDP and you learned it, very small number of sets and actions. And you learn the probabilities and the rewards. Then what can you do? You could directly solve the Barman equation. But that will hardly ever be in reality. There will be hardly ever a problem worth solving where you could directly solve the Barman equation. So you have to now do other kind of planning approaches. The one thing that is remarkably better is to replace the real world MDP. The real world is an MDP. Whatever you're trying to learn is an MDP. You have approximated it. You found the best substitute MDP. But you can use this MDP to generate as much experience as you want by sampling. So from this approximate MDP, there is no shortage of experience. Why? Because this is just a computational problem now. It's not about putting a robot or something out there to collect the data. So if collecting data was a problem for you in your situation, finding a model allows you to generate as much data as you want. This is the whole point of this kind of method. So you can generate from your model, from your probability distribution, the next state. You can generate from your probability distribution the next reward and generate as big a sample as you want. Once you have generated enough sample, you could, for example, use this sample to a Monte Carlo method to find the optimal Q function. Okay, so this is very simple. It might look obvious and trivial, but it is amazingly efficient. But what is the catch in this? Is there a catch in this process? Yeah, so the real MDP might be biased. The MDP that you're using, so your approximate solution, this thing that you have picked, might not be as close to the real thing. It could be biased, and you might get more experience as you get more data now. What do? So this thing is a static thing, right? It doesn't change. But it was trained on some experience. Now suppose there is more real experience. Now there is more real experience. This algorithm is no good for that. Because whenever you have a new experience, you have to then train the neural network to get a new set of these things. Then you use this new MDP to generate experiences again, and then you generate your policy. So if you have a continuous real life experience, which is not very fast, this is typically a robotic issue, but also in many other domains where you have so you have a website where you're trying to sell things, but initially only a few customers are coming, or sometimes a lot of customers are coming, and how, say, Netflix gives you your next, viewing, what do you call it? Suggestion, exactly. The next suggestion, that algorithm should dynamically update as time goes by. As they have more and more data about you and people like you, they have more and better understanding of the real world. So they should change their model as time goes by. And as the time goes by, you have changed your model. And then you do this Monte Carlo again. Every time you change your model, you generate the sample, you do this process again. This things like you have done two separate things, two completely separate issues. So what is the most interesting thing about model-based RL, and which I'm not going to cover today, because as I said, I have a conflict of scheduling today. So the most interesting thing about these things, this is a very simple and efficient thing as long as you don't update the MTP very often. So you collected some data, you made your model, and then you use this model, then it's a very efficient thing. But if you are collecting a data at some sort of a random but possibly unpredictable rate, like in a website or a robotic situation, then you want to do these processes simultaneously. So that's called integrated model-based learning. Okay. I don't think I want to cover this today because it will not be enough time for me to do that. Let's just think about this in something. So what you could do is, one way of most obviously integrating is you get new data, right? You're generating sample data. You add the new data in the sample data and let the Monte Carlo learn with the new data as well as with the sample data, right? So this is one obvious solution to the problem. One obvious solution is just mix the two things up. Let the sample data be generated, let the real data be coming. But what's missing here? What is missing here? You have never updated your MDP with the real data, real new data. Okay? So this nice solution is also something that people implement. But it is still one step less than what you would ideally want to do. All right? So that is pretty much, I think, what we'll start next time. And maybe we'll do some theoretical background of these kind of model-based learning as well. But I think, as I said, I have to go today, be somewhere at 11 o'clock. So I will have to stop the class now, right? And so maybe we'll continue with this next time. Okay. So this is now becoming easy again, right? The policy gradient was probably the hardest of the stuff. So if people are what do you call it, afraid of KL divergence or whatever, it's gone. But I think if you want to do any data science or even pure math or whatever, it's good to know about these things. Either ways, there's just no way of running away from density learning. All right, so I have to speed up because you guys have any questions? No. Yeah.
No, about what.
Okay.
So about the project, so do both member have to submit in Moodle or like just one of them?
One is good. Just in the submission, write all the names.
Okay.
I mean, it's obviously a lot of data, and I will have to then always make sure. Oh, if I have someone double or someone once, I would prefer if every team just gives me one file, because then I can just print every file I have, for example, right? So, and there are suggestions for the interviews where I would like to talk to two people separately. Just ask what you did and what your partner did, and how did you choose problems, something like that, right? Nothing too complicated. Just want to see how people have done their things. So, good. All right. So see you next time.
I have a question about the project.
Yeah.
I'm doing this Google Maps thing that I wrote you some weeks ago.
Yeah.
And so it's basically a discrete word problem, and I'm solving it with Q-learning and an epsilon 3D policy.
Okay.
But I mean that works fine for a very small grid word. But as soon as it gets bigger,
yes,
that I mean,
explodes.
It needs, I don't know,
infinite. Yeah, it needs something. Yeah. I know that problem. It exists, so it's fine. You tried and it worked. So what I want is not something industry scalable. I want to see that you have understood the algorithm, you have understood the problem. Your problem at least works in some setting. Somewhere it diverges. It's fine. I'm completely fine with that.
So
you should also write this in your report that it works for such and such scale, it explodes at such a scale. That's fine.
So I should rate the stick at a small grid word.
Yeah, so you should kind of in your report maybe say that it works as long as the grid is not that big. Or it works well as long as grid is 5x5, whatever your specifics are.
Yeah. Okay.
So you write that in your report, like it will work till this limit, because I'm not doing an industry course here. I want to see people have understood the algorithm and can implement it and understand what the problem with the algorithm is. Right?
Yeah.
Because what in real life you'll have to do is not something that you learn in any classroom, not just in my classroom. Anybody who pretends to tell that I will teach you real life problem in a classroom can only teach you one real life problem in the classroom, which does not apply to 50 people. Right?
Yeah.
So I'm not going to waste my time or your time with that.
No.
So as long as you've tried, as long as you understand the problem, as long as your code is clean, you should expect a very good grade. Okay. That is what I mean.
What's so how to solve this problem with the large grid word?
So I think a direct Q-learning epsilon greedy will not work. You have to at least go to some sophisticated versions of SARSA in the Q-learning.
Okay.
And maybe even a simpler SARSA might not work. You have to do a little bit more optimization.
I guess, some kind of functional approximation.
Yeah, and of course, if you put it in any kind of neural network, it will manage it.
Okay.
So if you put
that's really
but see,
advanced.
I don't want to push anybody to that. That's not the goal of this course.
No, but I'm interested.
Yeah, sure. I mean,
Something
see, I am
like-
giving all this my talks. I say I don't, as a mathematician, it would suffice for me to say there is a parameter theta. But I try to give a picture to you where you should think this theta is by drawing a neural network in it. Always, right? This is my way of saying, when you think of the neural network abstractly, only think of a parameter. When you have a mathematician giving you just a parameter, think of it as a neural network.
Okay.
Right? There is these are one and same thing in modern world, as if current world. I mean, it will change as things evolve. So